Okay, hello everyone, and welcome to the first lecture of EE 532 on communication network optimization. We will be following chapter 2 today from the book by Shrikant and Ying. This chapter deals with several topics on the mathematics of internet architecture. We will start by discussing convex optimization quite briefly and see applications of convex optimization to resource allocation problems, specifically resource allocation problems that are stated as utility maximization problems. And then, lastly, we will talk about the stability of dynamic systems, which probably we will postpone to the next lecture. Now, how do we define a convex set? As many of you know, a set in n-dimensional real space is convex if for any alpha between 0 and 1 and any points x and y inside the set S, alpha times x plus 1 minus alpha times y is in the set S. In other words, take any 2 points in S, take their convex combination, alpha x plus 1 minus alpha y. This convex combination has to be a point in S. Okay. Now, as you sweep alpha from 0 to 1, this convex combination sweeps a line segment from x to y clearly. So this alternatively states that take any 2 points in the region S, join them. The line segment that joins the 2 points has to be inside S. So that's a more pictorial description of a convex set. Okay, so that also explains why this blue region here would not be a convex set. Because clearly, if, for example, you join this point with that point, the line that joins them is outside S. So in such a case, there is a way to convexify the set by including the minimum set of points that bring the result to a convex form. And we call the resulting set a convex hull. The convex hull of a given set S, denoted by CO of S, is the smallest convex set that contains all the points in S. Okay. In other words, the convex hull of S contains the points in S and contains all convex combinations of those points, as described completely in this equation. So summation alpha I xi such that xi is in S and alpha i's are coefficients that are between 0 and 1 that sum to 1. All such summations, meaning all such convex combinations, live inside the convex hull of S. Now, what is a convex function? A convex function defined from a convex set in n-dimensional real space to the set of real numbers is a function that satisfies this inequality for any 2 points x and y in S. So given 2 points x and y in S, if you take their convex combination, meaning if you pick a point in between and if you compute the value of the function f at that in between value at that point, the function, the value of the function taken, the value taken by the function at that point should not be above alpha times f of x plus 1 minus alpha times f of y, which is the convex combination of the value taken at f and the value taken at y. Okay, in other words, the line segment connecting the 2 points x comma f of x and y comma f of y should be lying above the plot of f of z, pictorially speaking. So a convex function essentially looks like a bowl, like a cup looking up. So the negative of a concave function is a negative of a convex function is a concave function. Okay, so a function is concave if and only if negative of that function is convex. An affine function, on the other hand, is the sum of a linear function and a constant. So an affine function satisfies the definition of a concave function as well as the definition of a convex function. So an affine function is both concave and convex, but it is neither strictly concave nor strictly convex. So how do we check convexity? The first order condition for a first order condition for checking convexity is using the first derivative. If the function is differentiable, okay, and this is not the true for all functions or for all convex functions clearly. But if the function f is differentiable and the derivative f derivative is non-decreasing in S, then f of x is a convex function. If the derivative is increasing in S, then it is strictly convex. Okay. Another first order condition deals with the gradient. Okay. Now suppose we, f is differentiable and we compute the gradient. You know what the gradient is. You differentiate with respect to all the components of the vector. That is with respect to all the basis vectors of this vector space. In other words, with respect to all the dimensions, and you obtain this vector in n dimensions, which is the gradient. Now, the gradient multiplied by the distance from x to y is delta f times y minus x. And this gives us essentially the point at which we arrive on this tangent that we evaluate, that we draw at point x. Okay, so when you add to point x this rise and progress along this tangent, if the function is convex, then what you arrive should be below the value of the function. So that this inequality states that. Okay, so a convex function is always above any tangent drawn to it at any point. Okay, and that is the idea behind gradient descents, for those of you who have heard of gradient descent. Now, a second order condition for checking convexity is using second derivatives. In general, when we have a vector valued function, we will compute the Hessian matrix. The function f is strictly convex if the Hessian matrix is positive semi-definite over all values in S. So the Hessian corresponds to the second derivative if we had a one-dimensional function. Okay, and positive semi-definite corresponds to being positive in the scalar case. In the matrix case, of course, we work with positive semi-definite. If it is positive definite, then we're talking about strict convexity. Now, so far we have understood the definition of convexity and how to check for convexity. Okay. Now, there is an interesting theorem that you may not have heard before, and it is going to be used in several results later on in this course. So that's it's a good time to discuss that. It's the strict separation theorem. So suppose S is our convex set in Rn, and suppose X is a point that is not in S. Okay. Okay, so there is X that is outside of the set S. Okay, separation theorem says that essentially, basically, you can for any point y, you can find a separation between X and Y in the following way. For every point Y that is in S, if you compute this inner product BIYI, okay, beta I, YI, then the result is less than or equal to the inner product beta I xi minus delta. So there is a constant delta, and there exists a vector beta that you can find such that this will hold. Essentially then, there is some separation between any point that is inside of the set S and any point outside of the set S. So this we can revisit later. I strongly recommend, in order to understand this theorem better, I strongly recommend you read the proof of the theorem in the textbook. Then it will make sort of maybe more sense, and you will get more intuition about it. Now let's now that we are equipped with the basics, let's talk a little bit about convex optimization. First of all, think about an unconstrained optimization problem. We have a convex set S, and we would like to maximize the value of a function over the set without any constraints. Okay. So first we can define local maxima and global maxima. For any function f of x over some set S in Rn, x star is said to be a local maximizer or a local optimal point if there exists an epsilon that is positive such that f evaluated at x star minus delta x is less than or equal to f of x star for delta x such that delta x is less than or equal to epsilon in magnitude and x plus delta x is in S. Okay, what does this mean? So first of all, this says in words that if x star is a local maximum, then wherever you go away from x star, the function value is only going to get smaller. It's not going to increase. Okay. So mathematically speaking, going away from x star means going to x star plus delta x. Okay. So basically, we want this delta x, we think of this delta x to be a small displacement, okay? Because we're not talking about a global maximum here at the moment, we're talking about a local maximum at this point, okay? For a local maximum, there has to be some small displacement such that if you go only by that much, the value of the function can only decrease. We're not giving guarantees for any epsilon at this point. We're saying, well, if you get displaced just a little bit from x star, the function will decrease or stay the same. It will not increase. Okay. Now, if x star is a global maximizer, then this will have to hold for any displacement, any amount of displacement. Meaning x star is said to be a global maximizer if no matter where you go in the set, the function value is not going to increase over what it is at the point x star. Okay, so in the rest, whenever we say maximum or maximizer, we refer to a global maximizer over the defined set S. Are there any questions here? So there are some corollaries of the definition of a local maximum and a global maximum. So if the function f is continuous over a compact set, what is a compact set? S is closed and bounded, meaning it contains its boundary. Okay, this is not an analysis course. You do not need to worry about these limits, but so basically we sort of we're doing an overview and taking the results that we need from real analysis without going into depth. So S is closed and bounded, meaning S is a compact set. If F is continuous over this set, then F will have to achieve a maximum over this set, because you may think this is quite intuitive. There has to be some maximum value. There may be, it does not have to be a unique point, but there has to be a maximum. Because why do we need S to be closed? Because if F is not closed, then toward the boundary, S can keep increasing and increasing, so we won't have a well-defined maximum point that is achieved inside S. Okay, but if F is a compact set, clearly there's going to be some maximum or maxima over the set S. Now, further, if F is not only continuous, but also differentiable, then, okay, here's the important point that you've been using for many years now in many courses. Any local maximizer in the interior of S will satisfy the gradient at x star being 0. Okay. Now, conversely, if f is a concave function, not conversely, sorry. If f is a concave function over S, concave function, you know, a function that looks like a downward-looking cup, then this gradient being 0 at x star is also sufficient for x star to be a local maximizer. So this is actually why we are working with convex functions and concave functions, because we know how to maximize convex or concave functions. We know how to maximize concave functions. When a function is concave, then you can easily find the maximum by finding the point that satisfies zero gradient. Similarly, when a function is convex, meaning cupped looking up, you can find the unique minimizer by finding the point with zero gradient. Okay. Now, moreover, if f of x is concave, then a local maximizer is also a global maximizer. This is wonderful, right? In general, multiple global maximizer may exist if f is not concave. If f is not strictly concave, in fact, there may be constant points. So multiple global maximizers may exist, but if f is strictly concave, then the global maximizer is unique. Everything that we said, we're at the moment saying for the maxima of concave functions, but results 2.1.6 and 2.1.7 also hold when you change maximum with minimum and concave with convex, right? So that is given as result 2.1.8. Now the next result, and we are stating all of these results with no proof, but I strongly suggest that you read the proofs in the textbook. If f is differentiable over the set S, and x star is a maximizer, okay, then the gradient at x star times the displacement delta x is less than or equal to 0. For any feasible direction delta x, and for any delta x such that when you get displaced by delta x, you are still inside the set S. So, so this means that wherever you go, okay, the amount of difference that you incur in the function is going to be negative if you start from the maximizer. So clearly, you could do gradient ascent. You could go along the direction that where these differences are positive, and you would end up at x star, the maximum point, right? So further, if f of x is a concave function, then x star is a maximizer if and only if for any displacement such that delta x such that x star plus the displacement is inside S, then when you go from x star by displacement delta x, the result is less than or equal to 0. Okay, so all of the previous things that we discussed were about unconstrained maximization or minimization. So now what happens when there are constraints? At this point,